This video is an introduction to elastic energy. It's called Spring, Sprang, Sprung. It says success is how high you bounce when you hit bottom, and that's by George Patton, who's a famous general in World War II. So let's take a look at Spring, Sprang, Sprung, and it says the learning goals are that you be able to identify the factors that affect elastic potential energy. So a lot of times you'll see elastic potential energy as PE and then elastic, which is too long for me, so I usually express it as EPE, which stands for elastic potential energy. You also need to be able to relate work and elastic potential energy, so you need to say where does it come from, just like we did with all the other energies. And you need to be able to use the formula, which we said was PE elastic equaling 1 half kx squared. So, spring, spring, sprung. If you suspend a greater mass on a spring, it will increase the force that is exerted on the mass because mass and weight go together, and it will actually, as a result, it will increase the length that the spring goes. So the gravitational force means that you have more energy that's stored. If you increase the force, there's more energy that's stored in the spring. If you were to graph the relationship between distance and mass here, you would get a relationship. And if you were to get a certain relationship, you can actually graph these things where you've got force and displacement. So force and displacement, you can actually find what we call the spring constant. And in fact, it would have to be force and displacement. Okay, that spring constant is a measure of the stiffness of the spring. Okay, it's how difficult it is to stretch it apart. A trampoline spring is very difficult to stretch apart, but a slinky is very easy. So those would have different what we call spring constant values. Now, if you were to instead find the area under the curve here, the area under the curve would represent the energy because you've got force and displacement, right? So that's another indication of work. You would have 1 half of force times distance would equal the energy that's stored. And you say, well, wait a second, I thought that work was just force times distance. If you look in this particular case, you don't have the same force. You have a different force here than you have here. So instead you have to take the average of the forces. And that's what you're doing by doing this 1 half the force times the displacement. So that's kind of where it comes from, this idea that we have the elastic energy equation. And the elastic energy equation is PE elastic equals 1 half kx squared. So you've got this idea that this K value was once again the measure of the stiffness of the spring. It's measured in Newton meters. So anytime you have newtons divided by meters or something along those lines, it's the K value. This X value actually represents the displacement. Now it's really important that you get the displacement right because a lot of the times you'll see, okay, you have a spring that is initially 1.2 meters and then it is compressed to zero point 0.8 meters. And people will say, oh, okay, well, zero point 0.8 meters is what it is, so that's got to be the displacement. And it's not. Remember, the displacement is the change in position. So I was 1.2, and now I'm 0.8. So really, my displacement in this case would be 0.4, or what the actual compression distance is. A lot of times it will say it is compressed by 0.4 meters, but you need to be aware of this so that you can actually solve for what the compression distance is. So just like we had before, conservation of energy is going to apply here as well. In the first case, we said if you push a car, it will make the car move faster. You could have work equals the change in kinetic energy. In the second video, we said, okay, if you take this work and you raise a box up, it increases the gravitational potential energy. Well, the same thing happens with a spring. If you push on a spring, the work done in compressing that spring is equal to the elastic energy that is stored in the spring. So we get an example. You have a 1200 Newton force that is exerted on a spring with a spring constant value of 480 newtons. How much work is done on the spring when it is compressed by 10 centimeters? So I'm trying to figure out what the work is done on the spring. Okay. Remember, work is equal to the elastic potential energy that the object gains. So it's going to have zero potential to begin with, and whatever you do work on the spring, it's going to equal the elastic potential. So a lot of the reason for this is this can get kind of confusing for some people. They say, well, I'm supposed to take the force and multiply it by the distance. And that's not the case in this particular example. The force is irrelevant information. What you're supposed to do is you're supposed to use the spring constant to go ahead and solve for this particular displacement. So how much work is done on the spring? You would solve for the elastic potential energy. You have the K value as being 480 newtons per meter, and you have the displacement value as being 0.01 meters. You should have recognized that it's in centimeters and done the appropriate conversion to where it is 0.1 meters, not 0.01, but 0.1 meters. You can now say, okay, the work is equal to the elastic potential energy, which in our case is 1/2 k x squared. Now, the reason why you can't use the force here is because the force is not going to be constant whenever you're compressing the spring. And that's one of the things is when you actually push on a spring, it's never a consistent force to move the spring in. So even though it's 1200 newtons probably on average, or maybe that's the maximum force, you have no way of using that for sure whenever you're dealing with a spring. So now you say work is equal to 1/2 kx squared, or 1/2 of 480 times 0.1 squared. So whenever you do this, you would multiply it out and you end up getting a number of 2.4 joules. So there's not a lot of energy stored in this particular spring because it's not moving very much and it's got a pretty low spring constant value. The next example says, what is the spring constant of a spring that compresses 0.4 meters when 1200 joules of work is done on it? So in this case, we are trying to figure out what the K value is. And remember, a lot of times this work and elastic potential energy term are used interchangeably because the work that I do on it is equal to the energy that's stored in it. So now I can say the X value, or the displacement of the spring, is 0.4 meters. I know that the elastic potential energy equals the work, which equals 1200 joules, and that allows me to solve for the K value. I use the equation EPE equals 1/2 kx squared, and or 1/2 of 1200 times 0.4 squared. When you multiply all that out, you end up getting a number of about 15,000. Oh, excuse me, plug that in wrong. It should say 1200 over here and k over here. So now in order to solve it, what you would do is you would multiply these things out. So you do 0.4 squared and you get 0.16, and then you multiply it by 1/2, and that's 0.08. So now you would have 1200 equals 0.08 k. Okay, you get that by combining those terms. Divide both sides by 0.08, and when you do that, you get a number of about 15,000 newtons per meter. The last example says how much elastic energy is stored in a 64 newton per meter spring that stretches 0.35 meters. So this is about a slinky. A slinky is stretched by its own weight of the spring. It has such a low spring constant value. So you're trying to figure out the elastic potential energy that's stored in it. And you would say, okay, the K value is 64 newtons per meter. You have the X value is 0.35 meters. The equation is EPE equals 1/2 kx squared. And then at this point you would just substitute your values in. You would say, okay, EPE equals 1/2 of 64 times 0.35 squared. The most common mistake is people forget to square the displacement value. So whenever you do that, you end up with a value of about 3.92 joules.